Hi, I'm Professor Afshar at Glendale Community College. This is Physics 101, Lecture 9. In this lecture, we'll discuss vector arithmetic. This topic is covered in Chapter 3 of our textbook by Surway and Jewett. In our previous lecture, we learned about vectors. Vectors are important because many important quantities in physics, such as velocity and force, must be represented by vectors and not scalars. However, a single vector by itself is not very useful. We'd like to be able to combine vectors together. Specifically, we'd like to be able to do arithmetic with vectors, much in the same way that you can do arithmetic with ordinary numbers. At some point in elementary school, you learn how to add and subtract numbers. You learn how to multiply and divide numbers. You even know of some more complicated operations like differentiation and integration. It turns out many of those same operations can be carried out with vectors. Although in this class, we're really only interested in just a handful of operations that can be described as vector arithmetic. In particular, we'd like to be able to add a vector to another vector. We would like to subtract a vector from another vector. We would like to be able to multiply a vector by a scalar, and remember, scalars are just the ordinary numbers that you're familiar with. And eventually, we'd like to be able to multiply a vector by another vector. It turns out each one of these operations can be done in two ways. There is a geometric method for each one of these operations, and there's an algebraic method for each one of these operations. The geometric method is nice because it gives you a pictorial understanding. You understand the concept behind these operations a little bit better, and it's generally better for an intuitive comprehension of the problem. The algebraic method is important because it gives you precise numerical results that are useful for calculations. We will talk about both methods. So as we present each one of these operations, we'll present them in the geometric method and the algebraic method. Eventually, you need to be comfortable with both of those. Let's start with the geometric addition of two vectors. Suppose you have two vectors v and w with some random orientations and random magnitudes. What I want to do is add these two vectors together. In other words, I'd like to find a third vector which represents the sum of v and w. To add the two vectors together, we must follow a very specific recipe. The first step of the recipe says place the tail of w on the head of v. In other words, move one of the vectors so that its tail coincides with the tip or the head of the other vector in this manner. You can always move vectors around. However, in doing so, remember not to change the orientation of the vector. So don't change the direction in which it's pointing. And also don't change the magnitude. So long as you are preserving the magnitude and orientation, you can always move vectors around in space and drop them off anywhere you want. For the purpose of addition, you have to set up the vectors in this particular configuration so that the tip of one or the head of one coincides with the tail of the other one. Step 2 instructs us to connect the tail of v to the head of w. In other words, we're going to basically connect the remaining open ends of these vectors, and the vector that we obtain in this manner is the sum that we're looking for. So vector v plus w is simply the tail of v connected to the head of w. This procedure should make sense if you think of vectors as a set of directions. In our previous lecture, we talked about how the x and y coordinates of a vector essentially instruct us to take steps in the x direction and in the y direction to get from one end of the vector to the other. A similar thing is happening here. When we talk about the sum of v and w, we're essentially talking about following two sets of directions back to back. Vector v tells us to start at this point and move to the other end at this point, and then vector w instructs us to go from this point to this point. If we follow those two sets of directions back to back, we get the orange vector, which tells us to go from here, the very beginning of that journey, to this point here, which is the very end of that journey. If you want, you can also place these vectors on a graph paper and talk about the components of these vectors. We'll talk about the components in a couple of slides. Next, let's turn to the geometric subtraction of vectors. Once again, we have two vectors labeled as v and w, and I would like to find the difference between these two vectors. In other words, I'd like to calculate a third vector that represents v minus w. Once again, I have to follow a precise recipe. The first step of that recipe says place the tail of w on the tail of v. So we're moving the vectors. It doesn't really matter which one you move. You can move either one, so long as they end up in this particular configuration. Notice the tails are now coinciding. When we were adding vectors on the previous slide, we were setting up the vectors so that a tail coincides with a head. Now we're setting up the vectors so that the tails coincide together. And then we connect the remaining two open ends. Specifically, we connect the head of w to the head of v, and the orange vector that we get represents the difference of v and w. Here you have to be a little bit careful about which way the vector points. The orientation of the vector is determined by the first vector in the difference. In other words, if you're trying to calculate v minus w, then the difference must point towards v. But if you're trying to calculate w minus v, then the orange vector should point towards the w. So the orange vector, the difference vector, is always oriented to point towards the first element of the difference. If you want, you can place this entire thing on a graph paper or a grid and talk about the components of these vectors. And we're going to talk about the components on the next slide. So we've been talking about the geometric addition and subtraction of vectors. Here I want to talk about the algebraic addition and subtraction of vectors. The algebraic method allows us to get numbers, allows us to get Cartesian coordinates of vectors. When you want to algebraically add two vectors, the very first step should be to express the vectors in Cartesian representation. Remember, we have two representations for writing vectors down, the Cartesian and the polar. When it comes to the algebraic addition, you must work in Cartesian representations. This procedure does not work for the polar representation. Once you have the vectors in the Cartesian representation, the rest is relatively straightforward. You simply add the x components, and then you simply add the y components. Here are the same two vectors that we were talking about a couple of slides ago. As you can see from the graph, vector v has coordinates 5, 3. These are the Cartesian components of this vector, which means in order to get from this point to this point on vector v, I must go 1, 2, 3, 4, 5 steps in the x direction and 3 steps in the y direction, hence 5, 3. And for vector w, the coordinates are -3 and 4. So to get from this point to this point, I will have to go 3 steps in the negative x direction and 4 steps in the positive y direction, hence -3, 4. So here I've written v and w in their Cartesian representation, and now I'm ready to add them. I'm simply going to add the x components together. So 5 plus a -3 gives me 2. And then I'm going to add the y components together. So I have 3 plus a 4, which gives me a 7. So this vector here, 2, 7, represents the sum of these two, and it corresponds to the orange vector. As you can see, the orange vector has components 2, 7. In other words, to get from the tail of the orange vector to the tip of the orange vector, I have to go 2 steps in the x direction and then 7 steps in the y direction. So the geometric method and the algebraic method are consistent and they complement each other nicely. To reiterate, in order for this procedure to work, the vectors must be written first in their Cartesian representation. The process of adding x's together and adding the y's together is sometimes referred to as component-wise addition. Next, let's turn to the algebraic subtraction of two vectors. The procedure is actually very much the same. We express the vectors in their Cartesian representation. We subtract the x components, we subtract the y components, and the result is going to be the difference of the two vectors. So once again, vector v has Cartesian representation 5, 3. Vector w has Cartesian representation -3, 4. This is exactly like the previous slide. But now we want to take the difference of these vectors. So I'm going to perform component-wise subtraction. Here I'm going to subtract 5 and -3. More precisely, 5 minus a -3 gives me 8, and 3 minus a 4 gives me -1. So 8, -1 represents the difference of these two vectors. And if you look over here, the orange vector is indeed 8, -1. To get from one end of the orange vector to the other one, I have to take 8 steps in the positive x direction and 1 step in the negative y direction, hence 8, -1. So again, the geometric method and the algebraic method are consistent with one another. We have learned about the addition of two vectors and the subtraction of two vectors. It turns out it's also possible to combine scalars and vectors. In particular, we'd like to talk about scalar-vector multiplication. Here we're talking about multiplying a vector by a scalar using the geometric method. Suppose you're given some random vector v. It points to the northeast and it has some length v. We don't need to specify the length here. What we want to do is simply take this vector and multiply it by the number 2. So I'd like to find a new vector, which is 2 times the old vector. So this new vector 2v is going to point in exactly the same direction as v, however its length is going to be twice as long. So the process of taking a vector and multiplying it by a scalar changes the magnitude of the vector. If you multiplied it by 3, the vector would become 3 times as long. If you multiplied it by 17, then the vector would point in the same direction, but it would be 17 times as long. Now here I'm multiplying it by a positive number. What happens if we multiply it by a negative number, where the negative essentially flips the orientation of a vector? So a vector that is pointing north, when you multiply it by -1, will end up pointing south. A vector that points east will end up pointing west when you multiply it by -1. In this particular case, you can see vector v was pointing to the northeast, sort of upwards and to the right. When I multiply it by -1, I get a new vector which has exactly the same length as the old vector, but it's pointing exactly in the opposite direction, as if you have rotated the vector by 180 degrees. What would happen if you multiply the vector by -2? Well, as you can guess, the orientation changes by 180 degrees, and then the length also changes by a factor of 2. So it becomes twice as long, and then it points in exactly the opposite direction to vector v here. Here I've presented the geometric method of multiplication. Algebraically, you could do the same thing. We could say vector v has Cartesian coordinates 1, 1, and we want to calculate 2v. In other words, we like to calculate the product of 2, a scalar, and the vector 1, 1. To do that, we simply do component-wise multiplication. So we take the 2 and we multiply it by the 1, and then we take the 2 again and we multiply it by the other component. So in a sense, we're distributing the scalar into the parentheses. When we do that, we get 2, 2. The vector 2, 2 points in exactly the same direction as the vector 1, 1, but it's going to be twice as long. If you want to take the vector v and multiply it by -1, you do the same thing. You multiply the x component by -1, and then you multiply the y component by -1, so you're distributing. And what you get is -1, -1. This vector here has exactly the same magnitude as this vector here, but it points in the opposite direction. Its orientation is 180 degrees relative to the orientation of this first vector. We've talked about several operations involving vectors. We've talked about the addition of two vectors. We've talked about the subtraction of two vectors. We've also talked about how a vector can be multiplied by a scalar. As it turns out, you can also multiply a vector by another vector. Vector-vector multiplication is a somewhat complicated process, and it turns out there are two ways of doing it. One way of multiplying a vector v by another vector u is known as the dot product, also known as the scalar product. Today we will not talk about this operation. We'll save this operation for chapter 7. And then there is another way of multiplying two vectors, known as the cross product, also known as vector product. We'll save this operation for chapter 11. So for now, I just want to mention that it is possible to multiply two vectors, but the process is a little more complicated, and we'll save it for a little bit later in the semester. Let's finish this lecture with a practice problem. Vector A has length 4 and points to northeast, while vector B has length 5 and points to south. Express each vector in polar coordinates. As usual, when you're dealing with vectors, it's very helpful, almost necessary, I would say, to draw some pictures. Sometimes I'll give you the picture. Sometimes I'll expect you to draw the picture yourself on the test. In this case, vector A has a length of 4 and points to the northeast. That basically means halfway between the positive x-axis and the positive y-axis. Vector B has a length of 5 and points to south. That means that it basically points along the negative y direction at an angle of 270 degrees, although you can describe this same angle as minus 90 degrees. Once you have a nice picture like this for yourself, it should be pretty easy to write down the polar coordinates or the polar representation of these vectors. The magnitude of vector A is going to be 4, that's given to you, and its orientation is going to be 45 degrees relative to the positive x-axis. The magnitude of vector B is given to you as 5, and its orientation is 270 degrees relative to the x-axis. Express each vector in Cartesian coordinates. In our previous lecture, we learned how to convert back and forth between polar and Cartesian representations. Now that we have the polar representations of these vectors, it should be pretty easy to convert to the Cartesian representation. Remember, last time we learned that if you have the magnitude of a vector A and you have its orientation theta, then you could use a little bit of trigonometry, sines and cosines, to figure out the x component and the y component. And that's what I've done here. So if I take 4 and multiply it by cosine of 45 degrees, I will get 2.828. And if I take 4 and multiply it by sine of 45 degrees, I'll get, again, 2.828. For vector B, I'm going to take 5 and multiply it by cosine of 270. You'll get 0 when you do that. And I can take 5 and multiply it by sine of 270, and I'll get minus 5. For vector B, you didn't really have to do very many calculations. If you look at your picture, you can see that to get from the tail of vector B to the tip of vector B, in other words, to go from this point to this point here, you will walk 0 meters or 0 steps in the x direction, hence this 0 here, and you will take 5 steps, or you will travel 5 meters in the negative y direction, hence this minus 5. So for vector B, you didn't really have to do any calculations, although you can check your calculations using these equations if you wanted to. Question C, part C, asks us to express the sum in Cartesian coordinates. So we now need to do some arithmetic. We need to add vectors A and B and express the results in Cartesian coordinates. Since we already have each vector in Cartesian coordinates, finding the sum is easy. We just carry out component-wise addition. So we take the 2.828 and we add it to 0. and we take this other 2.828 and we add it to minus 5, and the result is going to be 2.828 in the x direction and minus 2.172 in the y direction. So this is the Cartesian representation of the sum of these two vectors. Part D of this problem asks us to express the sum in polar coordinates. Well, we already have the sum in Cartesian coordinates, so we now just need to convert these two numbers to polar coordinates. We learned how to do that in our last lecture. In our last lecture, we learned that if we have the x component of a vector and we have the y component of a vector, we can just square those, add them, and take the square root. In other words, we can use the Pythagorean theorem. So the 3.566 that you see here is simply the square root of this number squared plus this number squared. To find the angle or orientation of the sum, we need to take the y component and divide it by the x component. So here is the y component of the sum. Divide that by the x component of the sum, and then take the arctangent of that to find that the orientation of the sum is minus 37.516 degrees. Incidentally, notice that to find this final answer, I followed a very specific recipe here. So on an exam, I might just give you a picture like the one you see in the upper right-hand corner, and then I might simply just ask you to express the sum in polar coordinates. In that case, you have to know that you must follow this procedure. You want to write the vectors in polar coordinates, convert to Cartesian coordinates, add the Cartesian vectors, and then convert back to polar coordinates. You have to follow this procedure because if you simply took the polar coordinates and added them together, you would not get the right answer. Notice that 4 plus 5 gives you 9, which is not at all the number that we obtained here. Similarly, 45 degrees plus 270 degrees does not give you minus 37 degrees. So for you to get the right answer, you have to carry out component-wise addition or subtraction on the Cartesian coordinates. So these conversions are extremely, extremely important. These formulas that you see on the right side here are going to come up quite frequently. You'll probably use them literally hundreds of times this semester. So it's important for you to memorize these conversion formulas here and not have to think about them very much. You should be able to derive them with a little bit of trigonometry, but you should be somewhat fluent in the language of polar and Cartesian representations so that you don't waste a lot of time thinking about these formulas. And that's the end of this lecture. Thank you for your attention.